Alright, cycloalkanes, section 10.3. Cycloalkanes have two less hydrogens than the corresponding chain alkane. So an example of that would be hexane, which has a formula C6H14, which follows the general formula of an alkane, which is CnH2n plus 2. Whereas cyclohexane has the formula C6H12, which follows the generic formula for a cycloalkane, which is CnH2n. So, for example, if you had cyclopropane, it would be C3H6. So again, we follow the formula CnH2n. So to name cycloalkanes, to name them, you put the prefix cyclo to the name of the corresponding alkane. So it would be cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane, so on and so forth. Then you will place the substituents in alphabetical order before the base name, the same way you would for alkanes. So ethyl will come before methyl, butyl would come before both of those, etc. We follow the alphabetical order. And if you have multiple substituents, you will use the lowest possible set of numbers. And if you have a single substituent, so if you only have one substituent on your cycloalkane, you do not require a number. And we'll look at an example of that. All right, so moving along, over here you have some cycloalkane structures. So this just shows 1, 2, 3 different cycloalkanes. It shows cyclopropane, cyclobutane, and cyclohexane. So cyclopropane, propane, you'll remember, means that we have 3 carbons. So cyclopropane has 3 carbons in the ring. First, you see the structural formula, which is basically a Lewis structure. Then you see a condensed structure, which emits any carbon, which emits the carbon-carbon bonds. And then the last one is a bond line or a line structure, which just looks like a triangle, but that's how you would represent it. The next one is cyclobutane, so you'll remember that cyclobutane, so butane has 4 carbons. So following the formula CnH2n, the formula for cyclobutane must be C4H8, and if you count up all the carbons and hydrogens in the structural formula, you will see that there are 4 carbons and 8 hydrogens. Then we have the condensed formula, again followed by the line structure. There's not a lot of space here, but if we had cyclopentane, which has been left out here, okay, I'm not going to draw the condensed or structural formula, but the bond line structure or the line formula should be simply a pentagon like that, and it should have a formula of C5H10. And then lastly, shown on this slide is the is cyclohexane, which is C6. So it must be C6H12. And again, if you count up all the carbons and hydrogens here, you'll see that you have 6 carbons and 12 hydrogens. And there's the condensed structure and the line structure as well. And you can go on to cycloheptane and cyclooctane, so on and so forth. So more information about naming a substituted cycloalkane. You will so if we want to name the 2 cycloalkanes that are shown on this page, they're both shown in full Lewis structures here, both of these. You look at the parent chain. So for the first one here, you can see that I have 6 carbons in my cycle, if you will. So that's a cyclohexane. And for the second example, you can see that there's 5 carbons in the ring. Therefore, that must be a cyclopentane because you have 5 carbons. Next, you look for the substituent. In the first example, we have a chlorine. If I draw in all the valence electrons there, just for fun. So we have a chlorine atom, so that gets the prefix chloro. And on the other one, the cyclopentane, we have a methyl group, so that gets the prefix methyl. So if we put the whole name together, for the first one, we get chlorocyclohexane, and for the second one, we get methyl cyclopentane. And if you remember from the bottom of the first slide that I presented in this video, that when you have only one substituent, you do not need to give that substituent a number or a locant. So you do not have to say 1 chlorocyclohexane. That is incorrect. That is redundant. You do not have to include that information because if you think about it, when you have only one substituent on the ring, there's only one place that it can be. So there's no need to put a number there. Moving along to cis-trans isomers. So this slide gives you a little information about what cis-trans isomers are, and it says atoms of an alkane can rotate freely around the carbon-carbon single bond having an unlimited number of arrangements. So if you have a carbon-carbon single bond or a sigma bond in an alkane, you can make a molecular model of that and show free rotation around a sigma bond. In the next point, it says here rotation around the bonds in a cyclic structure is limited by the fact that all carbons in the ring are interlocked. And the best way to see this is to actually make a molecular model of a cycloalkane, and you'll see that you do not have free rotation around the carbon-carbon bonds in a cycloalkane. So based on this, you get the formation of cis and trans isomers, which are called geometric isomers, and those geometric isomers are a consequence of that lack of free rotation, that inability of the cycloalkane carbon-carbon bonds to rotate completely. So here we come up with a new definition, which is stereoisomers, and this is going to be an important word for Chemistry 102, and it says stereoisomers are molecules that have the same structural formulas and bonding patterns but different arrangement of atoms in space, and the key word here is space. So you notice that in this definition they're very careful about the wording. It says they have the same structural formulas and the same bonding patterns. That it means they're even connected in the same way, but they have different arrangement of atoms in space. And if you're like, well, how does that work? Well, we're going to take a look here. It says the cis and trans isomers of cycloalkanes are stereoisomers. So when we see cis and trans isomers on cycloalkanes, they would qualify as being stereoisomers whose substituents differ in spatial arrangement. So notice that word, it's not the word space, but now we're using the word spatial. So that word is going to be key in understanding what stereoisomers are. So let's take a look here at cis-trans isomers. So it says here two groups on the same side are called cis. So it says two groups may be on the same side of the imagined plane of the cyclo ring, or they may be on the opposite side. So if you take a look at the two examples at the bottom here, you can see that we have these two chlorines. We have these two chloros here, or these two chlorine atoms that are on the same side of the cyclohexane molecule. And if we look at the other example, you can see that they are on opposite sides of the cyclohexane molecule. So when the two chlorines are on the same side, we have to prefix the name with cis. So if we didn't know whether these two chlorines were on the same side of the molecule or not, we wouldn't be able to provide that information. But in this case, we can clearly see that both of these chlorines are below the ring. Therefore, we call the molecule cis 1,2-dichlorocyclohexane. And in the second molecule, you can see that the two chlorines are on opposite sides of the ring, and we call that molecule trans 1,2-dichlorocyclohexane. So these are examples of stereoisomers because they may be connected in the same way. They have the same connectivity of atoms, but they are geometric isomers because these two do not interconvert. Okay, there is no equilibrium here. In fact, I'm going to erase all that because they cannot interconvert with each other. So let me get rid of all of that. Okay, the only way you could get these two interconvert, and they wouldn't really be interconverting, would be by breaking a carbon-carbon bond. So these are two completely different molecules that would have different physical properties. So cis and trans, which are stereoisomers. So moving on to section 10.4, which discusses the conformations of alkanes. So it says here, conformations differ only in rotation about carbon-carbon single bonds. So this slide, there's a lot of information on here, but you can see that the first two molecules are molecules of ethane, and the second two molecules are molecules of butane. So you remember that ethane is CH3, CH3. So I'll just draw the condensed structure here. And butane is CH3, CH2, CH2, CH3. There. So the two conformations of ethane and butane are shown, or I should say two conformations of ethane and butane are shown. The first one is called the staggered form. So in both of these cases, the first two, these are the staggered forms, okay? They are more stable or energetically favorable because it allows the hydrogen atoms to be as far apart as possible, and therefore they are less crowded. So you can see here that the way the staggered conformations are arranged, all the hydrogen atoms are as far away from each other as possible. Again, just like a lot of things in organic chemistry, the best way to visualize this is by holding a handheld model. But hopefully you can see here that this hydrogen atom in this circle here is kind of like in between these two hydrogen atoms here. We'll have to look at a molecular model of that sometime in class. But you can see that if you were to rotate around this carbon-carbon bond such that, let's say, this hydrogen atom here was to move up, then you get what's called the eclipsed conformation. And this is much less stable because the hydrogen atoms now are very close to each other. And because of the electrons in this bond and the electrons in this bond being closer to each other, we get electron-electron repulsion, and therefore that makes the eclipsed conformation a higher energy conformation. Even more so on the molecule of butane, if we were to do a rotation around this bond such that you get this CH3 group coming in close proximity to this CH3 group, so that's these two groups here. They just circled one hydrogen atom here, but now you can see they're very, very close to each other, and that's a very high energy or energetically disfavored conformation. So these are called the eclipsed conformations. Again, the best way to visualize these is by holding a handheld model, but hopefully just by looking at these ball and stick models, the point gets across. So moving on from there, here it shows a couple of conformations of cyclohexane. If you look at the chair form of cyclohexane, so these are, both of these molecules are cyclohexane. Cyclohexane, I'll write down the molecular formula, C6H12. This one we call the chair form. This is the more stable form. And the reason why is because in this form, okay, in this conformation, this shape, all disfavored interactions are minimized. So it's just a simple way of saying that there is less crowding. If you look at the boat form, so you can see it kind of takes on sort of the shape of a boat here. You can kind of see like this maybe. Kind of draw the boat shape like that. Anyhow, in the boat shape, what happens is that there are some unfavorable interactions. For example, you can see that these two hydrogen atoms here on the top are pretty close to each other, much closer than any of the hydrogen atoms would be in the chair form. And therefore, that creates a little bit of electron-electron repulsion, and that's why the boat form, although it can exist, is not nearly as stable as the chair form. Another thing I'll point out about the chair form is if you remember the tetrahedron, so if you remember that carbon likes to adopt a tetrahedral shape where all the bond angles are 109.5 degrees. I've just drawn the molecule of methane here. So what's interesting is that every bond angle in the chair, so if I pick any bond angle at all of the bond angles are 109.5 degrees, and thus all repulsions are minimized. I'm not going to go through every bond angle in the boat form, but I'll just leave it like this and say that there are some bond angles in the boat form that are not 109.5 degrees, and thus, again, that just gives you more evidence as to why the boat form is less stable than the chair form. In the last section of Chapter 10 that deals with alkanes are the reaction of alkanes. So any alkane, whether it be an alkane or a cycloalkane or any other hydrocarbon, so it could be an alkene and an alkyne, but we'll save that for Chapter 11. So alkanes and cycloalkanes, they can undergo a couple of types of reactions that we're going to look at in Chemistry 102. The first one is essentially oxidation, which is really just burning them. So if you've ever burned a hydrocarbon, meaning if you've ever driven an automobile and you've burned gasoline, well, you've helped that gasoline to undergo oxidation. So that's an oxidation reaction. So we're going to look at oxidation of alkanes and cycloalkanes. The name of that reaction, the fancy reaction or the chemical term would be combustion. And you've probably all heard of an internal combustion engine. And the other reaction, so we'll put number 1 for this one, and the second one that we're going to look at is a reaction with a halogen, usually chlorine or bromine, and what's called a halogenation reaction. And if you remember from Chemistry 102, the diatomic elements, you'll remember that chlorine is a diatomic element and exists as Cl2, and that bromine is also a diatomic element and it exists as Br2. So let's take a look at the first reaction, at combustion. So the majority of the reaction of alkanes are combustion reactions. So a combustion reaction is nothing more than an alkane. So in this case, it's showing methane combining with oxygen. The products are always going to be carbon dioxide and water. No exceptions to that. So everything that we're going to look at in Chemistry 102 is always going to be complete. We're always going to look at complete combustion. So you will always take a hydrocarbon, add oxygen, and the products will always be carbon dioxide and water. What you'll be responsible for in Chemistry 102 is being able to balance these kinds of reactions. So if you look at the combustion reactions that were provided as practice problems from the textbook, make sure that you know how to balance those equations. The second type of combustion reaction is an incomplete combustion reaction. So incomplete combustion reactions produce carbon monoxide and water. And you've probably heard of carbon monoxide. Sometimes it's referred to as the silent killer because it's odorless, and if it can result in death if you were to actually breathe in too much carbon monoxide. You've probably heard of carbon monoxide poisoning. Anyhow, it's good to understand incomplete combustion and that it produces carbon monoxide, but I will not ask you to balance any of those equations. So we could even write that down. Will not be asked to balance. So will not be asked to balance. But you will have to balance complete combustion reaction. All right, so getting close to wrapping it up here. The last kind of reaction, or the second one, is halogenation. So halogenation is simply a type of substitution reaction, which is a reaction that results in the replacement of one group for another. So if you think about the word substitute or substitution, it makes sense that you would just be substituting one group for another. That's all substitution is. So the products of this reaction are an alkyl halide, so that will be some kind of alkane that has a halogen attached to it. So we get an alkyl halide or a haloalkane, and then we get a hydrogen halide. We're only going to look at halogenation with chlorine or bromine, so the hydrogen halide could either be HCl or HBr. This reaction is important to convert unreactive alkanes into many starting materials for other products. So if you think about the synthetic or the utility of an alkane and what it can be used for, well, alkanes can be a starting material or a precursor for many more reactions than just, or several more reactions than just combustion. But halogenation is a good way to take a compound like an alkane that is quite unreactive and convert it into starting materials that are reactive in order to make other products. So halogenation of alkanes only occurs in the presence of heat or light. So you might remember from general chemistry, the Greek symbol that's used to represent heat is delta, like this. And then for light, oftentimes we use H nu to represent light. So if you remember from Chemistry 101 where that comes from. All right. So the halogenation reactions are, you take an alkane and you add a halogen. The only two possibilities for Chemistry 102 are Cl2 or Br2. You use light or heat. You get an alkyl halide and a hydrogen halide. And the hydrogen halide in our case would have to be either HCl or HBr, depending on whether you use chlorine or bromine. So here are some examples. These are just three really nice examples that are shown here. So the first one is methane plus bromine gives you bromomethane plus hydrogen bromide. If you go back a couple slides, what did I say? A halogenation reaction is nothing more than a substitution reaction. So if you think about it, what we're doing is we're taking hydrogen, and I'm going to draw the Lewis structure of Br2, which is this. All you're doing is you're substituting the hydrogen atom for a bromine atom. So you can see that you lose a hydrogen atom and the bromine atom gets added. So what are you left with? After you add this bromine atom, you're left over with bromine and hydrogen, which combine to give you hydrogen bromide. So that's the substitution reaction. So that's one example. The next one is just showing ethane plus chlorine, and you can do the same thing. You replace one of the hydrogens with one of the chlorine atoms. So what would you be left over with? You'd be left over with a hydrogen atom and a chlorine atom. They will combine to give you hydrogen chloride. One last quick example here, cyclohexane. This is just showing the two of the bonds to hydrogen. Of course, there are other bonds to hydrogen in the molecule. This is just shown for instructional purposes. Again, you're replacing one of the hydrogen atoms with one of the two chlorine atoms. So what would you be left over with? The hydrogen atom and one of the chlorine atoms. So there's three wonderful examples of a substitution reaction, namely three different halogenation reactions. So here are some questions from chapter 10 that I recommend that you try before the first exam. It would even be a good idea to try these right after you've listened to this video.